So this is meant to follow on from Will's talk. So let's recall, so in Will's talk, which was higher order logic and topoi 1, so we gave an alternative characterization of topoi using a collection of objects which acted like power set objects, parameterized by objects of your topos, rather than a sub-object classifier. And that's essential for this talk because the way we're going to extract a topos from a higher order logic is actually going to involve power set objects rather than a sub-object classifier. It's just, I guess, for historical reasons, that's how type theories were set up. Okay. So this entire talk is going to follow Lambek and Scott. Basically part 2, section 1, with the exception that my type theories and therefore my topoi don't have natural numbers objects, right? So they're just, it's a little different. Okay, so the next 20 minutes will be an extended definition of a type theory. For us, type theory is synonymous with higher order logic. Higher order because there's a type of propositions, basically. So roughly speaking, there's an omega or a power set objects in the logic. Okay, so what's a type theory? A type theory is a class of types including, well, yeah, given what I just said, that's a little awkward. Yeah, actually, let me revisit that. So what we're actually going to have in the type theory and therefore in the category is both of these, but the way that the role that's played by the omega is a little different to what we might expect. So that's why we need the approach in Will's talk. Anyway, we'll see. So omega should be thought of as the type of propositions. Yeah, okay. So really the distinction is that we're not going to talk about in the type theory directly exponentials, right? So the type theory won't have exponentials in it, it'll have power sets, and we'll construct the exponentials in basically the same way Will did out of power sets, and that's why we arrive at his definition rather than the original definition of topoi. Okay, so I'm going to say how we get this class of types, but for the moment that's one of the ingredients, and we also have a class of terms of each type. Including countably many variables of each type. And finally, for each finite set of variables, a binary relation entails X on the set of terms of type omega. All free variables of which lie in X. Okay, so that's more or less just a sketch of the outline of the definition rather than really the definition. So I have to explain what I mean by terms. Again, just like in lambda calculus, terms will be alpha equivalence classes of preterms. I have to make sense of what free and bound variables are. I have to tell you what the valid constructors of terms are and the valid constructors of types. Maybe it's worth giving sort of the global outline of how the definition is going to go, because it's going to take up a long time. So what I'm going to do next is give you some of the basic constructors of types from the atomic types. I'll give you the valid constructors of terms. And then a type theory will be a class of types which is closed under the formation operations, which include the basic ones, but possibly, basic ones being the following. So if A, B, and types, A cross B and PA are types. There may be other type formation operations, so there are many different type theories. The sort of basic or pure type theory only has these formation rules, but in a general type theory there may be others. Okay, so then I'll tell you now the similar basic term formation operations. There may be more term formation operations than the ones I'm about to describe. And then there will be a condition that terms are, or preterms at least, are precisely those freely generated by the variables and these term formation operations. Okay, so as I said, we're going to first define preterms. So part of the data of a type theory is a given set of basic preterms. Which includes, but is not limited to, the variables. This star, which is of type 1. And true and false of type omega. There is a set term formation operations, which includes the following but is not limited to the following. So as usual, I'm going to write T colon A means T is of type A. Is a preterm of type A, perhaps I should say. Okay, so variables are preterms, star is a preterm, true and false are preterms. Okay, so we can form pairs. So we think of this as a subset, right? So then we can form the membership term, which is a proposition. Yeah. Okay, so if we have, so it's usual to refer to preterms of type omega as formulas, right? So I'll just do that. So if phi is a formula and x is a variable of type A, then x in A phi is of type PA.
Assume that if phi doesn't have x free, then that's just, well, if phi is just a tautology that doesn't have x free, then it would just be all A, right?
That's right, yeah.
And if phi is a contradiction, it doesn't have x free, then it would also be nothing.
That's right, yeah. Yeah, I mean, so the book, for instance, writes phi bracket x. I always find this to be a bit of a weasel notation, in a way, right? Of course, that's what we're thinking of, but it doesn't actually mean anything, right? I mean,
yeah, I mean, if it was something like x is in A such that y is in Z, that's kind of weird.
Yeah, of course, we're mostly interested in the case where x occurs as a free variable in phi, that's true. Yeah, but I don't impose any constraint like that. Okay, then we've got the basic logical operations on formulas. So we have and, we have or, and we have implies. Things like not we'll define as constructions using, for example, implies and false in a second. Okay, so if phi is a formula and x is a variable type A, then we have for all and exists. Okay, so that's it. So those are the basic term formation, preterm formation operations. I'm not going to be able to keep the entire definition on the board, so we're just going to have to refer to the notes as we go, I think. So, class of preterms is freely generated from the basic preterms. By the term formation rules. So this is being a little imprecise because I'm not really saying exactly what a term formation operation is. In particular, if there's other term formation operations, they need to come with a rule for, which occurrences in there are bound, right? So for instance, these term formation operations here come with the data that this thing will make any occurrence of x inside here bound. So I think that's all I need though. So a term formation operation would be some sort of expression together with the information of variables becoming bound. This is sort of easy to make precise sense of. I do it in the notes. Just sort of inductively construct all the possible terms from the basic terms, and there are no coincidences that aren't just purely syntactic ones. Okay. So one defines in the usual way the free variable set and how that's modified by each of these constructions. I think maybe it's not worth writing them all out. I'll just say, so In the case of B1, the free variables of bracket A comma B is the free variables of A union the free variables of B. It's the same with the membership. The free variables of that comprehension, x in A such that phi, is the free variable set of phi minus x. And similarly for all and exists, and the free variable set of the logical formulas is the free variable set of P union the free variable set of Q. Okay. And in the following, whenever I say an occurrence of a variable in a preterm, I won't mean these. Or that up there. All right, so whenever I say substitute for an occurrence of, or an occurrence is free or bound, just like the lambda, the x in lambda x, yeah, so it's the same. Okay, so by the usual rules, we decide whether a given occurrence of a variable is bound or free. Okay, definition. So alpha equivalence is the equivalence relation on the set of preterms, which is the smallest equivalence relation, closed under all term formation operations. Sort of has the obvious meaning. I don't think there's any real point writing it out. That all makes sense, right? Such that, and then the actual meaningful part is what happens with B3 and B5. So such that for any pair xy of variables of type A and any formula phi now this preterm is alpha equivalent to this one. As usual, provided the bad thing doesn't happen, right? So provided no free occurrences of x appear in phi such that a y in that position would be bound. So that is, when I do this rewriting, no occurrence of y becomes captured by that.
You just insist that there's no y free.
In phi, you mean?
Yeah.
No, but there could be a for all y which is just pointless, that is just sitting there waiting to capture a y if it wanders into its territory.
Yeah. You never do these.
Yeah, don't do anything stupid. Yeah. And the rest of them for all x. All right, so Okay, and then the term is an alpha equivalence class of preterms. Okay, so one of the things that's pretty interesting about type theory, at least set up this way, is how equality is defined. So,
Yeah. Well, it's kind of weird.
yeah, this is sort of novel from the point of view of a set theoretic, the usual way we'd set up set theory, right? Okay, so here's some abbreviations. So, P, a formula, not P, is just an abbreviation for P implies false. P formulas, this is the obvious meaning. So equality is interesting. So this is for two terms of type A. Singleton. I mean, the singleton's actually a kind of complicated construction once you unravel the equality, right? Oops. Yeah, no, that's right. Then is this a unique? I mean, actually, it's good that we had this talk after Will's talk, because you sort of appreciate, I mean, the exists unique and the singleton sort of looked a little complicated from that point of view, right? And there's sort of good reason for that. That's sort of because it is complicated, at least in this version of type theory, right? Okay, so exists unique. I'm going to use that later. Oops, bracket. These things, so alpha and beta of type PA. All right. So usually what we would do in, say, lambda calculus is now introduce, when we don't have function application here, and we don't have beta reduction, and we don't have beta equivalence. So basically all the content, I mean, basically this is nothing at the moment, right? It's just a bunch of symbols. All the actual content of the logic is now in this third component, which is this entailment relation. That's what actually says what these things really mean. Okay, so, but I've defined now types and terms, right? So notice I didn't say anything about the types being freely generated by the term formation operations, type formation operations. It could be other things. Okay, so entailment. Now, the thing that we have to process about entailment is what the role of this X is actually, right? Apart from that, it just looks like fairly normal sequent calculus kind of stuff. That will become apparent sort of in the example that's on page 7, I think. So entailment is a set of tuples, P, Q, X, where P, Q are of type omega, and X is a finite set of variables. Possibly empty, and where the free variable sets of P and Q are contained in X. And so P entails with X, Q is just a shorthand for P, Q, X is in E. Okay, so then we've got 1, 2, 3 families of rules for entailment, which is to say, so the type theory is, as I said, a collection of types, a collection of terms, but really it's a collection of basic terms and term formation operations, because the terms are freely generated. It's also an entailment relation. So the entailment relation is part of the data, but it's required to satisfy some constraints. Okay, so as I said, there's 3 classes, so C1, C2, and C3. C1 is structural rules. I'm going to give them all numbers because I want to refer to them later. So C11 is just the axiom rule, which is to say that PPX is in E whenever this makes sense, that is, whenever P is a term of type omega and its free variable set is contained in X. Okay. Modus ponens. Okay, so this is the usual sequent calculus style. The current audience is perfectly happy with this, I suspect, but for the camera, let me say. So if PQX is in E and QRX is in E, then it must also be true that PRX is in E. You're allowed to add anything you like to the context. Okay, no constraint on the y, right? Just any variable. The interesting one is this one. So what's the condition here? So y is a variable, that's clear. B is a term of the same type. Such that it doesn't have to be a closed term, but it must be true that its free variable set is contained in X. Now this is all up to alpha equivalence, so just by moving ourselves around we can assume that no free occurrence of a variable in B actually becomes bound when we make this replacement. Right? So we do so. Okay, so that's just specialization, I suppose, right? Okay, so that's the structural rules. Logical rules. Actually, here's a little bit of a wrinkle. So if you look at C24, I couldn't quite see how I got from that to knowing the same thing was true without anything on the left-hand side. C24. So maybe I should say the notation. So we're going to use this notation later. I was going to introduce it. Okay, so entails with nothing means entails with empty set. Entails with nothing on the left-hand side. In principle, this should be an element of omega, a term of type omega, right? That just means true. So, well, I'll save my comment for when we get there, I guess.
You have the thing. So your comment is so the first clause one before you can't do the second thing, right?
Sorry?
No, just go on.
Yeah, let's debate it when we get there. Yeah. Okay, so I have that, and I have this for any p. That makes sense. So we have an and if and only if these two are true. Okay, that also makes sense. C2, 3, same on the left with an or. Okay, I can fit C24 in there as well. Okay, so C24 says if I have P entails Q implies R, that should be the same as when P and Q entails R. The problem is I don't know how to show that P and true entails P and vice versa, and one of them is sort of clear, I guess, which is so which one's clear? I'll have to think about it for a second. But yeah, I couldn't see how to, I mean, I want to use this to be able to get that, you see.
Yeah.
And I could do it if I knew sort of implies P, right?
Yeah.
But I can't even get that.
Yeah, that's a good point, actually.
I mean, I've got P entails P, but I can't move it over unless I have an and on the left, right? So I played with it for a little and I couldn't quite get it to work. So probably it's okay, but I don't quite see right now. So we're going to add one extra bit, which is just the empty version of that, which is basically just assuming that P and true is the same as P. I think we should be okay with that. C2, 5. All right, so this is for all. 6 exists okay, so I had one tiny example there. So that's how do you prove P and Q implies P? All right, so this example is just meant to indicate the idea of a proof tree, right?
Yeah.
Okay, so where are we getting to? P and Q entails for any set X for which that makes sense. So the final step is going to be from this using, which one's that? C24, right? And how am I getting this? So this is the addendum to C24. This was whatever, C21. This was modus ponens, C12. All right. Okay, so that's the second class of assumptions about entailment. And then the third is what Lambek and Scott call the extralogical axioms. C31 is comprehension. So this basically effectively says what the set comprehension introduction term, the introduction of that term, what its content is. So this thing is always in curly E whenever x and y are two variables of type A and phi is any formula, and the hypothesis, I guess, is as usual that replacing, did I get x and y around the right way here? I think so.
Yeah, you're replacing each.
Yeah, that's right. Yeah, so where no copy of x, if it was replaced for a copy of y and phi, would become
that's right. Basically, you're checking whether x satisfies the rule phi when you sub it into y.
Yeah, that's right. Yep.
That's the condition for x being in, that's it.
Yep. Okay, so that's comprehension. Extensionality. Oh, okay. Yeah, these are, I don't think we're actually going to use these today, so, and this one we'll use. Okay, so we think of these variables as standing for ranging over subsets of A, right? So given two subsets of A, if they have the same elements, then they belong to the same things, right? Because the equals was Leibniz equality, which is, so if for all x in A, x in U is equivalent to x in V, then that implies U is equal to V. And remember, this was, I guess, for all t in PPA, U is in T if and only if V is in T, right? Okay. Is the reverse implication automatic? I mean, if they're Leibniz equal, does it follow they have the same elements? That's not clear to me right now. That should be true, right? Well, you'd feel like you'd want it to be true, I suppose.
Yeah, then it should be true.
This is extensionality for propositions. So if they this is the Leibniz equality. What? Yeah. This is Leibniz equality again, right? So this is saying, I mean, this means that for all z in p omega, s in whatever I said, z is equivalent to t in z, and this is the logical implication. So this says that proposition formulas are the same as subsets of omega, right? What do we, yeah, but these may have free variables in them, right? So they're functions, really, they're predicates, functions with values in omega, right?
Yeah.
So that's kind of interesting. Products. Yeah. So there's only one thing of type 1.
Yep.
There's no weird elements of A cross B. Right. Jesus, this is a lot of quantifiers. Leibniz equality implies pairwise equality. Which I guess is just a way of saying there's sufficiently many subsets of A cross B which are within the language, right? That you can distinguish. Alright, so that's it. That's a type theory. So what I want to get to next is defining the category which arises from this type theory and defining its composition rule in particular and sort of proving that that makes sense. The proof that it's actually a category and a topos will come next time. But in order to set up the category, So if you think back to Will's talk, right? So we only have power sets basically at the moment. We don't have function sets, so we're going to have to define function sets. And then, well, the HOMs in our category are going to be terms of type the function set. And the composition is going to be set up just as you would compose functions in set theory using some formulas. And then to actually get that correct, we're going to need the following sort of just kind of technical seeming observation. So we need the entailment relation is sort of parameterized over sets of, over the context X, a finite set of variables. And that's important. And this example from Lambek and Scott sort of shows why. Okay, so observe that we can always deduce this. For the following reason, so we can deduce it from this, and this came from this. Right, so this was the axiom rule. And then the for all rule allows me to interchange a for all with a thing with a context. And then I can cut that against something like this. And again, this comes from just the axiom rule on exists.
We don't want to be able to deduce that for all x phi implies there exists an x with phi. But you do if such an x exists.
Yeah, that's right. Something like that.
Or if there exist things of type x. That's what's kind of weird to me. Why wouldn't you just, why can't you just settle for not having that set of the?
Not at all, you mean, even with context.
Because surely the fact that it's, I mean, basically what this is saying is, if there exists such an x, and for all x phi, then there exists x phi. But when you say it like that statement's vacuous, right? Because in order to assume that such an x existed, you assume...
I'm not sure I follow.
Oh, no, actually, no, I see what you mean. No, okay.
So, yeah, I didn't find this obvious when I looked at it, but this example with unicorns is a good one for why you don't want it without a context. But I think, I mean, what you want, so why do you want an exists? Well, why do you want it for all? What you want is, what's in, which rule is it? The final rule of the structural rules, C14, right? So what you want is to be able to deduce from this. I mean, if it's true with some context x, you want to be able to replace x by anything, right? So if there's already a closed term of type whatever a, then you do want to be able to deduce this with x replaced by that closed term, which would just mean, well, so suppose B was a closed term.
I mean, it seems to me that the much more elegant solution is just not having the statement be provable.
This one?
Yeah.
Yeah, but how do you do that? I mean, you'd have to give up one of these rules above it, right? Which one don't you want? I mean, the treatment of for all and exist seems kind of elegant, right? Where you just sort of move them around, move them into the context symmetrically. Actually, I think this is kind of slick, really. Right? So this was C1 for.
Yeah, the fact that something in A exists means you can solve it in.
Right. So that means that from for all, we can deduce there exists one with phi. And that's not weird because we already know there's at least one thing out there of type A. Right? It would be wrong to deduce there exists something satisfying phi from for all because maybe this is empty, maybe there's nothing satisfying.
Yeah.
Right? That it's in A. And the example in the book is, what is it? So take phi to be, so A is the type of unicorns and phi is the predicate has horns, right? So you don't want to be able to deduce that there exists a unicorn from the fact that all the unicorns have horns. Yeah, but this kind of discussion sort of makes it clear that many of the choices that go into the setup here are sort of non-obvious, right? Like you have to be pretty careful to get all this right. Okay, so that was one example, and then I want to do a second example, which is proving that basically for all and exists are somehow functorial. So we're going to need that. Okay, so this is on page 10. So. Okay, so suppose we have two formulas so one entails the other in some context, then I want to be able to prove that there exists an x such that phi 1 entails there exists an x such that phi 2. Of course that has to be true, it's just a question of how we justify it from the entailment rules. We do as follows. Okay, so this step was just the left introduction rule for exists. This step here was a cut, where on the left I had this is a bit of a weird dance on the left, right? So we start with this, then we can introduce the for all, and then we use this expansion of the context from the structural rules to add in a sort of fake x. And then we cut that against oops. Oh no, sorry, this should be, no, I want to start with 2 here. Right, so this is my hypothesis. Look at this. This is what we just showed. Right, so we just did this.
Yeah.
Okay, so that cut gives us the next line, and then the introduction gives us the result. Okay. All right. Okay, so let me define the category. I should say. Okay, so let L be a type theory in the sense I just defined. So that is, it's a class of types, class of terms, and this entailment relation. So the category TL has well, the way we build a category out of simply typed lambda calculus is that we take the objects to be types, right? But that's clearly not the right thing to do here because we have predicates and, set formation sort of comprehensions, right? So whenever we have an object, we can also think about the elements of the object satisfying some predicate, and that may not be isomorphic to some other type, right? So we need the types to actually be pairs consisting of an object and a thing that cuts out a subset, that is a thing of type PA. So we think of those as sets, i.e., so they're pairs A, alpha, where A is a type, and alpha is a closed term, that is a term with no free variables of type PA. Now, that wouldn't still be quite right because we don't want to distinguish. The next point is kind of subtle, I think. So without this last line, the entailment relation wouldn't play any role in the definition of objects, right? So this is saying we identify two sort of subsets if they're provably equal.
Yeah, this makes sense, right?
Yeah.
Because there's lots of different ways of describing a given set, right?
Right. That's right. Yeah, if we didn't have this, then you'd have sort of the same set being sort of syntactically distinguished and giving you different objects, right? Actually, it's possible they'd end up being isomorphic even if you didn't do this. Okay, morphisms. Let's do that somewhere else. So objects are somehow sets in this type theory, and morphisms are functions. And we just follow our nose to define that. I.e., so a morphism from a pair really we need to talk about equivalence classes, but that's a total pain. So, really we mean equivalence classes of such pairs. So a morphism between two pairs is a closed term of that kind. So obviously we're thinking of a graph such that it's provable that f is contained in alpha cross b. I haven't defined what this means, right? So let me do that now. So if alpha is a term of type PA and beta is a term of type PB, alpha cross beta means the following term of type PA cross B. It is Z A cross B such that there exists an X in A, there exists a y in B such that x is in A, y is in B, z is in B. X, y. Right, so that is a term of type PA cross B. Okay, so it must be provable in the type theory that f is contained in that, and it must be provably functional, that is, for all x in A, in the domain of f, there must be a unique y such that that's true. Okay, so this has the expansion I described earlier, and the rest is just as it is, right? And this similarly has the expansion I described earlier. Okay, so a function is a closed term modulo the similar sort of relation, right? So modulo the relation that okay, so that's morphisms. So usually we'll write equivalence classes of these closed terms, that is morphisms, as lowercase f's, and a representative closed term of that morphism we write as bar f. Okay. Yeah, the way I'm going to use it, I really mean a term, so I mean a representative, yeah. Okay, so that's a set. Then we need the composition rule. So what does that say? It says given two morphisms, F and G, composite G circle F. So what do I have to give you? I have to give you a closed term, right? Well, once I've defined this, then I'm going to write G circle F for a representing closed term. So let me just define that closed term. And this is just the usual way you would write down set composition. So it's the U in A cross C such that exists an X and exists a Z, open bracket, U is equal to X cross Z, and there exists Y such that XY is in the here we have to think a little bit about representatives to be careful, right? Okay, so what am I actually saying here? I'm saying take two morphisms, choose a representing closed term for the second one, choose a representing closed term for the first one, then write down this term. First thing I would have to prove is that this is provably the same term as the term I would get if I'd chosen different representatives. That's even more boring than what I'm about to do, so we won't do that. But that, you know, should be straightforward, right? Yeah, I think that's okay. All right, then at least we have a well-defined equivalence class up to this equality of closed terms. But we have to check a few things, right? I mean, this is, a morphism is not just the closed term, it's a closed term for which these propositions are entailed, right? So, lemma. Okay, so to check this as a category, we have to do more than this, but to just even check that this is a well-defined morphism, we need to check that that closed term satisfies those two rules, right? And what am I going to do? I'm just going to do the first one, I think. Yeah, that's the proof. So I'm going to show the first, which is to say that G circle F is contained in alpha cross gamma. Now we're going to do this in basically full detail because, you know, you've got to do at least one thing at the beginning in detail, otherwise you're just futzing around. Okay, so we're just going to prove this the usual way we would prove it in sets, right? But we're going to be careful about which entailment rules we're actually using and at which points. So, all right. What's the first thing we want to do? Okay, so what does this actually mean? That's an abbreviation for all t in P. Right, so this was a term of P. Where did it go? That was a term of type PA cross B, right? So that's what we've got to prove. So we need this at the bottom of a proof tree. But we know that having this is the same as having this in context T. Okay, so that's what we've got to get. So we're not actually going to write the proof tree because that would be extremely tedious. So we're just going to work backwards from this. Really, we're constructing the proof tree from the bottom up. Yeah.
Yeah.
I think I need that. Okay, so it suffices to show. Well, the introduction rule for implication means that I can prove that if I can prove that T in this entails in context T in that. just need to show this. Now the left-hand side is of the form T in a comprehension, right? Because this thing is just an abbreviation for this comprehension. The right-hand side is also a comprehension. So let me write let's write phi for all of that stuff. So this is all phi. Okay. So if you look back at the comprehension axiom, so the comprehension axiom is of the form entails and then a for all, but we can take that for all and put it in the context. And if we do that for this particular comprehension, we have this entailment, T in U T replaces U. Right, so that is in our entailment relation. Okay, so it suffices. Okay, so claim that's enough to show this. Why is that? So I want to show that. Yeah, okay, I see. So yeah, maybe I should, maybe at this point it actually does help to have the proof tree. So what's the structure here? So I've got this instance of comprehension. Which I've converted into this. That's just an and, so from it I can deduce the one-way implication, which goes from left to right. And then I can move, so this, okay, then I can move this over to the left, right? So if I can prove that, so the rest of the argument is now constructing the following proof. So if I could fill that in, then cutting those two together, I would have the proof I want, right? And this is what I needed to show. Yeah. Okay. So we just need to do this part. Okay. Okay, so this again was a set comprehension, particularly this one. So this is logically equivalent to, this with some substitution taking place. So, well, we've done one instance of comprehension in full detail, so now let's not do it again. So by comprehension, it suffices to show what? That the left-hand side entails this business with exists. So what happened there? Did anything happen? There should be a T, yeah. The T got substituted for Z, that's it. Okay, so that's what we're going to show. Here's where we go back and look at phi. So phi looks like that. Exists x, exists z. But this also looks like exists x, exists z, right? And this is where this exercise earlier comes in. So, well, by comprehension, So here's phi with t replacing u. So I just go in here and replace wherever u was there by t. And then I'll be looking at trying to prove in context T something that looks like these two existential quantifiers formula entails these two same existential quantifiers formula. So it suffices by that exercise to show that the formulas entail one another, namely that this business starting with the u, which became a t, and exists y and b such that x, y, and f, and y, z, and g entails in context, the context is enlarged to include the x and z. This stuff, so x in alpha, z in gamma, t equals x, z. All right. Well, now we use the the logical rules which tell us how to get entailments involving logical conjunction. So obviously this part will entail that part, so it suffices to prove that this part entails this part. And well, what I could write down here is something with an exists, but that's equivalent to the thing where I've moved the y into the context as well. So it suffices to show that x, y in f and y, z in g entails in context t, x, y, z, that x is in alpha and z is in gamma. So now we've reduced down to what's sort of the obvious reason why this statement is true. And well, if we want to prove this conjunction, we can just prove separately that xy in F entails xy x in alpha and yz g entails yz z in gamma. All right, and then what do we do? So, well, we know as part of the definition of this being a morphism, we have that, we don't quite have a proof, right? But we know that this is in the entailment relation. So we know that F is contained in alpha cross beta. We know G is contained in beta cross gamma. And if we unpack what those mean, so that's a for all, we can move that down into the context, etc., etc. And we'll see, once we look at this containment, that it means that if xy is in F, then x must be in alpha. Yeah, and then we do the same thing there. And those give us proofs of those two, and then we're done. Okay, so that proves at least that the first condition of G circle F, that it's provably contained in alpha cross gamma, is true. And then one would have to do a similar thing for the other condition. So that's sort of not quite, we haven't quite shown that TL is even a category, right? We'll do that next time. And then we'll put together in the sort of, I mean, you can see how it goes now, right? I mean, we're just gonna, the way we would prove sets is a topos, we just do it again, but it's twice as tedious. And then we'll prove that this is a topos. And okay, so we'll leave it there.